Okay, as I said, been thinking all weekend about what we'd like to cover today. And I've got enough thoughts to fill a semester. Still don't know what we're gonna do, but we're gonna do it anyway. Okay, so we're gonna kind of sketch the structure of the course. Okay? Just to put everything in the best perspective we can. I've got another board here where I did this a couple of years ago. And we might take a look at this one too. After we do this, okay? Actually, this is all multivariable calculus, but the back of one of these boards has statistics on it. Okay, so without looking at that, we're gonna do a quick review. So, and I think I've done this recently, but I'm gonna do it again. Constant acceleration. Gives you this. Okay. That's a general form of the equation of motion for uniform acceleration. Okay. And also V equals AT plus V naught. And we could say VL, or we could say V of T. Okay, so I'm going to use the F off here, leave the F off here. And write these pretty much the way your textbook does. Okay, because this gives you position as a function of velocity. This gives you velocity as a function. I'm sorry, gives you position as a function of time and velocity as a function of time. Now, by eliminating variables between these equations, you can get two more equations. One is that that's average velocity times time. And because velocity is a linear function of time, this is the average velocity. If velocity was not a function of time, this would not be the average velocity. It might be close to the average velocity, but it would not be the average velocity. And that goes back to the graph that I've drawn. It looks like this. The average velocity occurs halfway between here and here. Because why? Because this little triangle up here and this little triangle down here have equal areas. And the average velocity is the integral of the velocity divided by time interval. And it follows immediately, if you understand what the calculus is telling you, that if the function is linear, the average velocity is the average of the initial and final velocities on any interval. Now, I'm not going to belabor that. I'm not even going to, I might keep it there, but I might erase it later. You should be able to make that connection with this, because it tells you when you can and when you can't get the average velocity by averaging initial and final velocity. Okay, then you have okay, you put it this way. All right, now I treat x minus x naught as a single variable a lot of times, and you've seen me do that, so you might want to review that. But right there is everything you need to know about uniformly accelerated motion. As I've said, and I'm not going to write it down here because we want to get through a lot of stuff, if I know any three of the quantities, x minus x naught, which I call delta S a lot of times, T, V naught, VF, and A, any three of those five parameters or quantities allows me to determine the values of the other two. Okay. So that's it. And also, if it's angular motion, uniformly accelerated, angular motion, use omega, omega naught, alpha, T, and theta. And the equations are identical. They're reasoned out exactly the same way because if you start with the assumption that alpha is constant, then you just integrate alpha, substitute your initial conditions or whatever boundary conditions or whatever you have, and you get the function for omega. Okay. And omega naught is value of constant of integration, just like up here. I'm not going to go through the whole spiel. There are only a couple more sentences, but we'll skip them because you need to be able to fill them in. And I could ask you to derive either of these. It's just simple integration and understanding what V naught and X naught are. Okay. Is everybody here taking differential equations? Think? Oh, you've had it. I don't mean you've had it, but you've had differential equations. Okay. To say you've had it means you're finished. Forget it. And I certainly wouldn't say that about you or anybody in here. Okay. So anyhow, but yeah. You should understand how to use initial and boundary conditions in the solution of a differential equation. Well, you should understand it from first semester calculus at the level that we're talking about it here. So if you're having or have had differential equations, I have to assume that you can do that. And if you can't, email me. I'll give you a couple of simple exercises in outline, or go back to the first week or so of classes to see it done in detail. Okay. Okay. So that's all I'm going to say about uniformly accelerated motion. Now, the other thing I will say regarding uniformly accelerated motion is you have the equations of uniformly accelerated motion apply to the horizontal motion and to the vertical motion of the projectile. And you have to be able to use that. And you remember that time is the thing in common between the vertical and horizontal motion. That's the only thing that they have in common. And then you just solve the equations. And you probably want to review that because it's probably going to occur somewhere on the exam. Newton's second law, net force is F net is mass times the acceleration. And these are vector quantities. It applies in 2 dimensions, it applies in 3 dimensions, as well as it does in 1 dimension. Also, tau net equals I alpha. Net torque equals moment of inertia times the angular acceleration. Remembering that these are vector quantities, I commented on that in our last class. When you do a torque or an angular acceleration or an angular velocity or angular position, these are all vector quantities. And by the right-hand rule, they're perpendicular to the plane of motion. Okay. Now, what I said isn't quite right. It's not quite general. But for something moving on a circle, it is. Okay. And I won't ask anything that goes too far from what's on the circuit. You'll learn about that in multivariable calculus in the early part of the course. Okay. So we have then, here's Newton's second law in both linear and angular form. Fair enough? So you got to kind of know this structure so you know how to fit things together. Okay. Then substitute A equals F naught over M into the equation up here for B squared. Okay. Good, F net delta X equals delta KE, where KE is kinetic energy, equal to 1/2 mv squared. Change in 1/2 mv squared. Now you should be familiar with that. If not, review it. Okay. Just substitute F net over M and rearrange it so that you get F net. Yeah, okay, I did have delta X. And then the general form. You get tau net dot delta theta integrated equals change in kinetic energy. With the limits on your integral would be from, say, X naught to XF, or from theta naught to theta F. I'll even kind of pencil that or talk about it. You can't read it, but now I've got limits X naught, XF. Put my equal sign down here because I'm getting it. Okay. And this would be from theta naught to theta F. Momentum. Substitute A equals F net over M into this equation here, and you get F net delta T equals delta P. Note that work is a scalar. It's just numbered with units on it. Engineers, remember that things have units. Don't keep shooting yourselves in the foot by forgetting to do the unit calculations. You all are getting better at it, to the extent that I've seen it on stuff that you've submitted, which not everybody has, okay? But I was seeing signs that most of you seem to be starting to use units, okay? Remember that in grading an exam or test, I'm fairly intolerant of unit errors. Do your dimensional analysis, write your units into your quantities, because it makes it much easier to see what it is you're doing and keeps reinforcing the idea of what these quantities mean, rather than just a bunch of numbers that you plug into a formula you don't understand and hope it comes out right, okay? Now, when I say don't understand, I mean don't completely understand, because at this stage, most people don't completely understand all of the formulas, okay? And most people do completely understand many of them. So the more, the better, but there it is. Okay, so there's the idea of momentum. It's a vector quantity. Unlike work. Okay, now work is the same wherever it happens. The energy that's implied in angular quantity is every bit equivalent to energy you get for a linear quantity, although it has different effects on angular acceleration or angular velocity, angular position, than it does on linear. Okay, but it's still work. It's still energy that you got to take out of a battery or out of your glycogen supply. I said the other day, I think it's glycogen that you burn. Okay, I've always thought it was Cheerios, but it's glycogen. Okay. Yeah, I checked it with my wife, nurse practitioner for about 100 years. Okay, since well before your parents were probably born, and she confirmed that I was actually right for once. Okay, so it is glycogen. So the amount of glycogen you have to burn to produce energy, or the amount of gasoline you have to burn to produce energy in your vehicle, doesn't care whether that energy goes into rotation, like rotating your wheels, okay, or doing a fancy pirouette, or whatever it is you're doing to spin. You know, a cool spin move in a basketball game, right? Or do you just explode straight ahead? Now, I stopped exploding years ago, but you know, it can still move straight ahead. Still takes energy. Okay. Get the idea? Energy is going to change your kinetic energy and do work against friction. Okay. And the amount of energy is accounted for by the change in kinetic energy and by the work you do against friction. It's that simple. Now, somebody had a hand raised here, and I don't think it was a muscle spasm, so let's see what we got. Okay, I got a question. I'm not sure how work is in a vector quantity. And I think the confusion comes from the fact that we use vector quantities to get work, okay? But ultimately, we're integrating a dot product. Or if we have a constant force over a constant displacement, okay, we do a dot product. If our displacement's this way and our force is this way, we do the dot product, so we'll only get the part of the force in this direction. And of course, if you don't understand how dot product does that, you really need to meditate on it. Having been through linear algebra and a year of calculus, okay? You really have to understand that. I mean, if here's your work and here's your displacement, you take the cosine of the angle here, and that gives you the component of work in this direction. And that's the only, or the component of the force in this direction. And only that component does work. A component like this will change your direction, can move you in a circle like centripetal acceleration, right? Centripetal force. But it doesn't affect your speed. You can go around circles forever if you're not dissipating energy, and you never slow down because of the centripetal force. That's why orbits work. And that's worth thinking about and understanding. So in that case, so work is not a vector quantity. The other, my first response is going to be, well, okay, I give you a charged up battery that's got 500,000 joules of energy stored in it. Okay, what can you do with that? Well, you could put it in a reciprocating saw and it's going to go back and forth and you're going to get energy in harmonic, simple harmonic motion, basically. Okay. Or you could put it in a circular saw and you're going to get energy of rotation. Of course, you put that circular saw on a piece of wood and you got a whole lot of friction. Most of the energy from the battery goes into friction. Okay. You can put it into a drill and you're going to get rotary motion and all that. Now, if you're screwing something in, again, friction is going to take most of the energy. Make sense? Well, that's force is being exerted in all kinds of directions. There's no vector quantity to it until you put it in a piece of machinery. Or, you know, you're starving to death and I give you some food and all of a sudden you have energy to do whatever you need to do. Okay? Or just real low in glycogen, you really need some food. Now you can go out and run your 4.2 second 40 yards. Or do your 58-inch vertical leap. Okay? Now all those have directions, but they're different directions. Your force goes into whatever. Make sense? I wonder if anybody ever had a 58-inch vertical leap. I'd look at power lifters, especially power lifters in the lighter weight classes. Because the first thing you look at for a power lifter is their vertical leap, because you got to take that bar from here and get it up there. Okay. Those guys have significant vertical leap, but the bigger you are, the less you're at a disadvantage. Okay. A 5'6" NBA guard will have a vertical leap greater than a 7 foot, 340 pounder. Even though that 7 foot, 340 pounder can do some pretty darn impressive things. Quick like you wouldn't believe it, even though it doesn't look like it in the relative motion of an NBA basketball game. He looks slow. Put him in a neighborhood pickup game and everybody's going to be blinking. Where'd he go? What's he? Oh, there he is. You know, okay. If you've never been around a quick big guy, and I've never been around an NBA quick big guy in a game or anything, but yeah, it's kind of scary. Okay. Now, all that is out of the question, energy. You see energy going in all kinds of different directions. It's not a vector quantity. It can be used to produce a velocity or a rotation, each of which is a vector quantity. Okay. Okay, momentum. Now we have this. Now we have angular momentum. And substitute alpha equals tau net over I. Alpha and tau net are vector quantities. Into omega equals omega naught plus alpha t. And you get tau net delta t equals delta L, or L is your symbol that your text uses. And it's a pretty standard symbol for angular momentum. Okay. Now, big deal. You got to know what a closed system is. Energy and angular momentum are conserved. Now, you might object that we could have a closed system with friction within that closed system. Okay. Well, in a closed system, kinetic energy is not conserved. Okay. Kinetic energy is converted by friction into heat, but that's still energy. And we haven't talked about that, but we will early in January. Okay. That makes sense? So you got to understand what a closed system is. In angular momentum, again, that's a little more complicated. I'm not going to address it. Just understand that the systems we've looked at, angular momentum is conserved, but if you got friction thrown into the works, you can lose angular momentum. Okay. And what happens there is really an energy conversion question. Okay. Make sure you kind of maintain that perspective. Don't lose track of forces that can interfere with, say, conservation of kinetic energy. Well, this comes down to the work done by your net force is, well, now I need to think about what I'm writing. I'm writing it. Work done by your net force is your change in kinetic energy. Okay. Okay, now I want to make sure I write this carefully so you can actually use it. Okay, I just had to stop before I wrote something stupid. Okay. And this equals your change in kinetic energy. Work done by the conservative force is what? Equal and opposite to the change in potential energy. And I say, okay, I wrote something stupid here. F and C is work. The work done by your non-conservative force. Now I said negative U, I mean negative delta U, because the work done by your conservative force is equal and opposite to the change in potential energy, right? It's not equal and opposite to the potential energy. Remember, I told you you have to be able to recite that definition at the drop of a hat and to echo it in your head when you're thinking about energy conservation. Change in potential energy is equal and opposite to the work done by the conservative force. Don't forget that. And don't lose track of it, and always think it. Then you keep things straight. Okay. So this gives you delta K plus delta U is the work done by your non-conservative force. If you don't have non-conservative forces, then delta K plus delta U is 0. So delta K equals negative delta U. So tendency is for a loss of potential energy to be balanced by gain in kinetic energy. Okay. So there you have it. If your non-conservative force does positive work, example, spaceship wants to increase its orbit, so you burn your engines, speed up, and then coast for a while till your potential energy decreases to the point or increases to the point where you want it to. Okay. If you're trying to go to a higher orbit, you're going to increase your kinetic energy. So you're going to increase sum of kinetic and potential. But then you're moving away from the planet, so your potential starts dropping, or sorry, your potential starts increasing. Therefore, your kinetic starts decreasing. Stuff like that. You need to reason this out and understand what these equations are telling you in a variety of different situations. Does that halfway make sense? So you kind of grab on to this formulation. It's basically saying now, this is your mechanical energy. You can do work with a non-conservative force and increase or decrease your mechanical energy. And in mechanical energy, change of potential energy either goes into kinetic energy or into overcoming a negative work done by friction. Okay. You have to think through examples and do problems where you apply this in order to really understand it well. But it's a guiding principle. Okay, well, that's energy conservation. Momentum conservation. There's a P in energy, isn't there? Now there is, although you can't read it. And it can make it even worse. You know what it says. Okay. Now, coming off of momentum and angular momentum, force exerted by one on the other is equal and opposite to the force exerted by that other on the one. If we're both standing on skateboards and I give you a push, you're going to go that way and I'm going to go that way. If you outweigh me and the skateboards are of equal weight, mass, okay, if you outmass me officially, then I'm going to go faster than you are, but in the opposite direction. Okay. If heaven forbid, I'm carrying a football down field and somebody tackles me head on, if they have greater mass than I do, I'm going to tend to go backwards and they're going to tend to keep going forward a little bit. If I outweigh them, then it's going to be the opposite. Not my age either way, I'll end up in the hospital, but that's irrelevant because I'm not going to be doing that if I can help it. Okay. Equal and opposite forces. If it's two rotating systems, it's the forks that are equal and opposite. Because wherever they exert their forces, they're being exerted at the same position relative to whatever, but in this case, we would think relative to the axis or point of rotation. Okay? So you're going to get equal and opposite changes in angular momentum. Just like here, you get equal and opposite changes in linear momentum. It follows that the change in the momentum of one is equal and opposite to the change in momentum of the other. Why? Because F delta T, wherever the heck it went, is the change in the momentum. Ever write that down? Yeah, it's got to be. Yeah, there it is. Okay. This one, impulse momentum for objects in linear motion, impulse momentum for objects in rotational motion. So then we can write exactly the same equation. So L1 plus L2 is a constant vector. I put an arrow over constant here. It's constant, but it's not a scalar constant. It's a vector constant. When you're in angular motion, you got to remember everything's a vector. Same when you're in linear motion, but if you're moving along a straight line, you can kind of fudge that. You know, motion that way is a positive number, motion this way is a negative number. That makes them vectors, displacements, and so forth. Okay. So we've got all that. And when you're thinking through these problems, at first you ought to have all this stuff in front of you so you can see where you are in the scheme. So that you can wean yourself with the scheme and still think in terms of the scheme when you see it on the exam. Okay? When you're working a problem on the exam. What does this scheme allow me to do with the given information? It's not the question of what formula do I plug into, because you're likely to pull out the wrong one, especially if you don't do dimensional analysis. Okay? Which most of you don't seem to be doing, but some of you do. Some of you, and you're doing better. Try to get good at it in the next 3 weeks. Okay? So that takes us up to angular quantities, but of course, it doesn't tell us where this stuff applies and how it's used, but we've done a whole lot of stuff in lab about where these things apply and how they're used. Okay? And remember, I can give you lab data for any situation that you've had your hands on, or even some situations that you haven't, and ask you to do some analysis. Okay. And hopefully, when I do, because I will, certainly a chunk of the exam is going to be really tangibly based on things that you've measured and had your hands on and manipulated. those should be easier for you to think through because you've seen what happens. The other point of that is if you think through what you've observed in lab and how it fits into this scheme, it's going to strengthen your ability to do things even outside of what we did in the lab. Also recommend that you read problems in your book, especially in these last 3 chapters. Okay. Where nobody's really totally done what I said, although some people are actually caught up on it by now. I'm recommending you spend time every day thinking about these things so they sink in. Think in terms of this scheme. Now, the rest of the scheme we pretty much talked about last time, but I'm going to still summarize it. So I want to focus on orbital velocity or orbits and simple harmonic, or gravitational interactions, which are usually, if they're not here on Earth where we can just use a linear, a constant gravitational acceleration in a small area. But talking about things interacting in a closed system without significant dissipative forces, without significant non-conservative forces, unless we're trying to accelerate and decelerate. So, okay, so anyhow. Here's a big deal. This, okay? Because of the integral, the gravitational force dot dr. And actually, I think I used a different variable. What variable did I use? I used rho. I used the integral from R naught to infinity of this, which equals here it is in a nutshell. I did it in more detail last time. I think I know how to handle chalk by now. And here I've written R instead of R naught. Okay, because in general, we're going to use R for where you start. R is the same as R naught. I used R naught here so we wouldn't confuse it with the variable of integration. But we did it last time, and that's our potential energy. It's a potential energy relative to infinity. Then in a circular orbit, I'll use that. You get V equals GM over R, where G is the universal gravitational constant. I'll give you that on the final at 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Okay. Now, does that make sense? For bigger R, do you get a bigger or lesser V? Bigger or lesser? Further away from the planet, you get less velocity. Why? Because you have less gravitational force, you have less centripetal acceleration, and your R itself is bigger, and you put all that together, and you find out how V varies is the reciprocal square root of R. And that's an important thing. We'll note that V is proportional to the reciprocal square root of R, which means that if you know V at 1R, you don't have to go through the square root of big G, big M over little r. You can just say that V2 over V1 is the square root of R1 over R square root of R2. That could be handy. You know, if you're trying to get the test done in a reasonable time, it's a nice shortcut. Could save you a couple of minutes. And that's what I mean by the importance of proportionality. Y'all would benefit from being much, much better at using proportionality. And I've advised you, it's probably worth your time to spend an hour learning the basics of proportionality and variation. It takes no longer than that, even with, when I was teaching the course, liberal arts math, which I love teaching. It was a fun course to teach. You know, it's much lower level. Don't even assume algebra 2, okay? But you can teach people that only barely know algebra 1, proportionality in an hour to where they can do it. But then they're going to forget to review it for the exam and miss it, but they will know how to do it within an hour, okay? If they don't reinforce it, well, that's what unfortunately happens. You're probably exposed to it and didn't have to reinforce it. If you don't have to reinforce it, you won't. But you can use it to think through the meaning of every equation, almost every equation that you encounter in introductory physics, okay? So I complete it. All right. Well, that's the big deal. I'll just make a short statement that angular momentum is constant for two gravitationally interacting bodies or objects, since R12 equals negative R21 is radial. radial. And remember that Newton's law of universal gravitation tells you that the force of interaction is negative big G, big M, little m over r squared times a unit vector from one object to the other, which is radial. That's what I mean by radial. Okay. So you want to think through that. When you do this derivative of the potential energy function, you get the force function. You want to draw yourself some pictures. Draw yourself a picture of two interacting bodies. Draw the r vector, multiply it by this scalar quantity here, and reverse the direction of the r vector, and everything makes sense. Okay. When I say reverse the direction of the r, keep the direction of the r vector, but take the negative of the direction of the r vector. And it points from one mass toward the other. Now, next week, I'll probably take some time to draw some more pictures. I'll probably make up some situations for you to just think through. Don't do the calculations. Some really key situations where there are things I want you to think about how these various quantities connect. Because the better you know that, the better you're going to be able to adapt to whatever I throw at you on the fly. I'm not trying to keep it reasonable, but if it's unreasonable, then the grading scale will be a lot more lenient. Okay. If I make it too reasonable, then the grading scale's impossibly easy or impossibly difficult to achieve. Okay. Anyhow, you can go on from there. Okay. That's really the key to gravitation. The other thing is escape velocity. If I want my kinetic energy to equal the integral from R naught to infinity of the work done by gravity, okay? Now, if I want to get from here to infinity, with gravity pulling me this way, gravity's going to be doing negative work on me, right? So I better either do some positive work or have some kinetic energy, which would be a result of positive work from burning rocket fuel and blasting it out the end of the rocket. Impulse momentum takes it. Okay. So anyhow, I haven't talked about escape velocity. If you're reading your text, you've seen it. Delta K plus delta U equals 0. delta U from here to infinity is positive. So we can write this as 1/2 mv naught squared plus UF minus U naught equals 0. Somehow I've got the wrong sign on this. I'm going to rewrite it. Your delta K from here to there is going to be minus 1/2 mv naught squared. UF minus U naught is your delta U. So now we have minus 1/2 mv naught squared equals U naught. Remember that U naught is negative because potential energy is relative to infinity. Okay. So I just had the wrong sign on my delta K. We're going from 1/2 mv naught squared to 0 out there when we hit infinity, not that we never hit infinity. So you get negative 1/2 mv naught squared equals negative big G, big M, little m over R. We'll call it over R naught. That almost looks like an X there. Yeah, it certainly did to me a minute ago. So make sure we see that as 2 big G, big M over R naught. Now, how does that compare with orbital velocity? Well, if you've been working on this, and if you're saving work on this for the Thanksgiving weekend, okay. But one way or another, please get it done by next week so you understand what we do next week. Okay. The other thing I'll mention, I'm going to put the deadline for the final as late as possible. I don't know yet, so don't count on it, but it would be possible to put it on the Monday after exam week. Okay. So if you're desperate enough to suffer through another weekend of preparation, you might have that option. But as I say, I can tell you next week when I know what the deadline is. But of course, you've got plans for that weekend. They're going to make it impossible to use it. Just count on getting it done. But whenever an exam week, you need to be done. Okay. Okay. So anyhow, okay. Here's your V naught. It's this. Compare that to the square root of GM over R for a circular orbit. Okay. You need the square root of 2 times the velocity of a circular orbit at distance R naught to leave forever. Never come back. Okay. Now, when I say that, That would be if the Earth was an isolated system. You also got to worry about the potential energy changes due to the sun's gravitation, okay? Which is much less at the position of the Earth than there is gravitation. But eventually, if this is all you give it, based on the mass of the Earth and the distance from the center of the Earth, you're going to start coming back after a couple billion years. Okay, make sense? Because you got to do the big G, big M, little r naught for the distance from the sun, which is like 93 million miles or 160 million kilometers. Okay, so r is going to be a big number, but so is the mass of the sun. But still, we take the mass of the sun and divide by the distance from the sun. It's a lot less than what you get if you divide the mass of the Earth by the radius of a low Earth orbit. Okay. It's interesting to figure out how far you got to get from the Earth for the two to be equal. Turns out that's the Lagrange point, which is where the Webb telescope is sitting. So it has equal acceleration to the Earth and to the sun. And enough fuel to keep nudging it. Because there are little anomalies. You know, where's Jupiter? It's big, not nearly as big as the sun. It's not that close, but it does affect it. So does Venus and Mars, and even Mercury and Pluto and all those other things. Okay, that's interesting to think about. Okay. Now, does that make sense? It's a simple integral. You've already done the integral, so we don't need to do the integral again. We know what the result is. There's our potential energy function. Now, the thing that I talked about a lot last time is just that the potential energy function is kind of key in many situations, including some rotational situations involve a really neat problem that I made up yesterday that I would not put in all its entirety on the final, but I probably will mention next week. Okay, because it's something that's tangible. It just comes down to what's the difference between the high point and the low point of the end of a beam, if it's tilted slightly, either due to more mass on one end or due to the tilt of the table or whatever. And it's all you need is high school trigonometry to figure it out. But it's a little hard to think about. Okay, just something to look forward to. Simple harmonic motion. What we're talking here is about the minimum that I expect you to understand about the structure. The minimum I hope you understand. If you're pretty smart, as all of you are, and understand this well enough, you should be able to adapt to just about anything I would throw at you in the final. Although I could always think of something that I wouldn't expect you to be able to do. I might throw a couple of those on for extra credit, but okay. Simple harmonic motion. The key to simple harmonic motion is and we've talked about why that is. We've done that integral a couple of times. You just integrate negative kx over m from 0 to x, and you get negative 1/2 kx squared, and that's your change, negative equal and opposite to your change in potential energy. Okay. I'll even integral from 0 to x of negative k. I'll use psi because it's kind of like Greek x. We don't want to confuse it with our limit on the integral. Okay. Why is negative 1/2 kx? If your net force is negative 1/2 kx, why is negative 1/2 kx then conservative? What's the definition of conservative force? Okay, so I just said, why is this conservative? Then I pause and discuss and immediately got there, well, it's path independent. Why is this path independent? Because it doesn't give a hoot whether whether you're going this way or that way. When you're position X, this is the force. So you're swinging out in simple harmonic motion and you get to position X, you got a force negative 1/2 kx, which is back toward the origin. If you're out and swinging back in, well, you have force negative kx. Same force. Doesn't care which direction you're moving, it just cares what position you're at. Why then is friction not conservative? You get friction if you're swinging out, you get friction if you're swinging in. Be air friction, there's not much of it, but why is it different? Well, because friction's in the direction opposite motion, and it is not path independent. If your path takes you out, friction's acting toward the origin. If you're swinging in, friction's acting away from the origin. Okay, so make sure we understand that idea. Two ideas. Potential energy, change in potential energy is equal to the work, equal and opposite to the work done by a conservative force. Okay? And conservative forces are path independent. And I mentioned we generalize that to the fact that a conservative force is one that's a gradient of a potential function, which is just saying the same thing as this force here, the negative 1/2 kx force, is equal and opposite to the derivative of your potential function. Okay. And when I said conservative force is equal to the gradient, it's a negative gradient of your potential function, just like this is the negative derivative. Okay. And you can throw that away. It's a big deal. It's not that hard if you understand potential. Not everybody takes multivariable calculus will understand potential functions because not everybody takes multivariable calculus has had a physics course on them most have. Okay. Certainly in the engineering program, it would be very unusual here for you to be in multivariable calculus and not having had a physics course. Or at least be taking one concurrently. Okay. It could happen. All right. So that kind of is a synopsis. Everything got to know about simple harmonic motion, except for the other thing you got to know about simple harmonic motion. Okay. That's a vector function, actually. Okay. I mean, X is a vector, it's a displacement. And F net is in the opposite direction of your X vector, your displacement from equilibrium. Okay. So you just replace F net by MA, solve for A. Because you know to get your position, you just got to integrate A twice. Now, you're not going to consider in this course, you see how it adapts very easily. When you take multivariable calculus, you can see how it adapts to more than one dimension. This is written badly, but I've written it a number of times. X double prime equals K negative K over MX. And that's equivalent to X equals A cosine of omega t plus pi. omega is the square root of k over m. That's the essence of what you have to know about the equation of motion. This is your equation of motion. And if you take the derivative of your x function, you're going to get the velocity function, and the derivative of that's your acceleration function. Now, one of the problems I asked you to do 2 weeks ago, due 2 weeks ago, I assigned it 3 weeks ago, was verify that this is a solution to this equation. Okay? And then I gave you 3 or 4 other forms. You can replace cosine with sine. It's still a solution to the equation. You could use e to the I quantity omega t plus phi, which you should be familiar with from differential equations. And you get a solution to the equation. You could use cosine of omega t, you could use b cosine omega t plus phi plus c sine omega t plus phi. And it's still a solution, superposition, all that stuff. Okay? So there are many ways you can express this solution, but this would be sufficient. Or if you prefer to use the sine, depends on what you're modeling. For some systems, it's easy to model it with the cosine. And that might make you phi equal to 0, which makes it simpler to think through, although phi shouldn't throw you by much. Okay? But sometimes the sine is preferable to the cosine, makes things a little simpler, sometimes the cosine, and sometimes it doesn't matter. It's going to be a little obnoxious because your phi is not going to be 0, but that's not hard to deal with. Okay? Just mathematically, it's pretty simple. In the unit circle position, basically then says if your reference point is on the unit circle, that angle theta equals a cosine of omega t plus phi. Okay. And this wouldn't be unit circle, it'd be radius A. And as I've demonstrated, talked about, as this point moves around the circle, the cosine moves back and forth down here, and the sine moves up and down here. Just because the definition, circular definition of the sine and cosine, it's an important thing to visualize. It allows you to check what you're doing, allows you to understand it in context. Okay. Now, the point then is, and some of the problems I've assigned really get to this, and some of you have done them successfully. I don't think people found those problems particularly difficult. If you did them and did find them particularly difficult, warn everybody else. Okay. But I think people did them pretty successfully. You take the derivatives of these, get your velocity and acceleration functions, and they're going to confirm what you get from your potential energy function and energy conservation. Okay. Well, we're out of time, but that's kind of a good place to stop. That really gives you pretty good detail about the scheme that you need in order to successfully navigate the final exam. But once more, I advise you, think in terms of this scheme. Write it out, have it in front of you when you first start thinking about things, wean yourself from it so that you don't need to have it written out, so it becomes as intuitive as possible. And when it gets to a point where it isn't intuitive, yeah, grab an equation and hope you got the right one. Okay? Because everybody's got their limits as far as the time you have to spend on it and your ability to think through it. Depends on your background, your overall aptitude, which is, you know, it's certainly adequate in everybody's case. Okay. So good luck. And I'll see you after Thanksgiving, and we'll have some more fun for the next week.